today I'm gonna show my kind of initial result on our recent results. So this means I realized yesterday, so if I speak pretty fast and then very short, my talk will finish within 10 minutes. So yeah, that's good compensation. But before my talk, so I put another slide because here, we are here in Tohoku, right? Tohoku area. And then let's take a look what happened beneath of Tohoku University, actually, where we are now. So this is a distribution of earthquakes. So these all black dots are hypocenter of earthquakes. And here, you can find triangles, right? Here, let's say it's volcanoes. So now probably we are somewhere around here, maybe. So beneath of Tohoku University, we have earthquakes. So not only big one, but also small one, many small one. And then this black line, very difficult to trace, but this black line shows a plate boundary. So this means, so we have big earthquakes along plate boundary, but these all earthquakes are not plate boundary type earthquakes, but all in intraplate type earthquakes. And then these are distribution. So this is very beautiful mapping. It's like textbook. Here we have seismic belt, right? Very difficult to trace, but anyway. So here's one seismic plane, and then another here we have another seismic plane. So we call double seismic zone or double Wadachi Benioff zone or whatever. So here we have two lines. And then Kita et al., so he's also from Tohoku University actually. So she suggested, especially for upper plane of double seismic zone, so this seismicity is relating to rock species or rock type. For example, so this is plate, right? Subducting plate. And the upper portion is, gabbro or basalt or oceanic crust, right? So here, and then we have metamorphic reaction. So with subducting the plate, the many reactions happen. And then originally we have basalt or gabbro, but with subduction, so it's no longer basalt. Now it's here we call blue schist, or more specifically jadeite lawsonite blue schist here. At this region, we have many seismicities. Then with subducting, so plate react more, and then dehydration reaction happen more, and then now at the intermediate these depths, we no longer have jadeite lawsonite blue schist, but now we have lawsonite amphibole eclogite, so different. Actually, chemistry is almost the same, but mineral composition is different. Then, if you go down more, so now we have eclogite. So it's also chemical composition is more or less similar, but mineral assembly is totally different. And then with these reactions, the plate releases water. Then, so here we have more water and more releasing water, and then here kind of releasing water still, but not much. And then if you have eclogite, it's kind of dry rock, so no water inside anymore. Then, so these like reaction and then seismicity is kind of relating, right? So here more water and more dehydration, so we have many seismicities. And then what with dehydration in progress, so earthquake seismicity tend to disappear. And then where that water goes is here, volcanoes. So water is released from the subducting plate, and the partial melting happens at the forward mantle, and then that melt or water goes up, and the partial melting happens somewhere. Then we have volcanoes. And then if we have eruption, so we have magma erupt, but also not only magma, but also water is also released from volcanoes. This means, so we have subduction and the volcanoes, right? And this cycle is kind of water cycle, material cycle as well as water cycle. So my kind of lifetime goal is how to reproduce these conditions in the lab. And then this is an example done by myself and Greg Frost when I was a postdoc. So here we collect this rock, actually mineral lawsonite, and then we squeeze low night. But so here it's stress, blue line is stress, the red is temperature, and then this is amount of sleep, and the horizontal axis is time. So we squeeze low night with increasing temperature. It's kind of simulating subduction. So with subducting, temperature increase, and then dehydration reaction happen. So we reproduce this kind of subduction in the lab like to increase temperature like here. So what happens with increased temperature, so rock get weak. First, we are now understanding or considering here, originally we have thermal weakening with increased temperature, rock get weak. Then weakening accelerate. So we probably this is due to reaction. So fluid released, and then effective pressure get down, and the rock strength also decrease, and then accelerate, and then we finally slip. Like here, this is black line, the big jump here, and then back to steady state slipping. So we think this is kind of reproduce of these kind of earthquakes. And then if you take a look at the sample, so here, so this is crack, and then here's actually shear zone, and then we found concentration of silica, which is dehydrated product. So actually the shearing crush grains, right? And then surface area increase, and the reaction enhance, and the more slip, and then grain crushing happen, and the reaction increase, and the more slip, and then finally the earthquake triggers. That was our story to trigger these earthquakes. So water and dehydration, reaction and deformation are coupled each other at the deep of the earth. But deep means like 100 or 200 kilometers in depth today. So this water cycle and the deformation of the earth and the seismicity all coupled. This is what I'm emphasizing in the take-home message. And then not only for seismicity, but also biology, this reaction and deformation could be a key. So here, actually this is not subduction zone, but probably, I don't remember exactly, but probably nearby Atlantic ridge, so mid-ocean ridge, I guess. And then we have chimney of carbonate here. And then, so this chimney means you have fluid, right? Which is different from the typical seawater. So these are kind of water stream at the base of the seafloor. And then where the source of this water is actually the deep of the earth. But deep means maybe 10 or 5 kilometers. But like the old water is flow along actually fault zone. Actually, deformation zone is worked as also fluid channel. And then we have like special water, like Shino Suzuki, yesterday's talk, she showed the special microbes along the cedars, right? So serpentinite kind of springs. And then like not only the cedars around the California, but also the nearby the ridge, yes, thank you, ridge. So we have this kind of fluid circulation, and which also kind of cradle the microbes. So this fluid circulation is also key to understand the microbes or like the origin of life. So and then I gonna back to Tohoku here. So here Miyagi Prefecture. This is Japan Island. Then after 2011 Tohoku earthquakes, we have another earthquakes actually. So which happened here. Actually, we have subduction zone, right? But the big earthquake happened far east of the trench here, which size of magnitude 7.6. So it's actually huge. But where it happened is kind of funny because this is depth here, and then probably this is profile of somewhere around here. So big earthquakes happen 20 kilometers in depth. And then some earthquakes happen even like 35 or 40 kilometers in depth. So probably many people know the thickness of the oceanic crust, right? So thickness of the oceanic crust is about 7 kilometers, roughly. So this means these deep earthquakes occurred within the mantle, actually. The subducting, outer ice region of the mantle. So, and then these are actually normal force, so kind of triggered by, induced by the extensional force. This means there's possibilities of water penetrated into deep of the earth, possibly 40 kilometers in depth. And then, probably I should back the first slide. So 40 kilometers in depth from the seafloor means actually somewhere around here. So these lower double seismic zone or lower plane of the double seismic zone could also be constrained by the hydration reaction, how deep water penetrated into the oceanic plate or oceanic mantle. Then, so this means, so if water goes into the mantle, so mantle, like shallow, it's shallow, like just 30 kilometers in depth to compare the Earth's radius, but it can be huge water reservoir to compare, even to compare the ocean, because the thickness or like height of the water is just less than 10 kilometers, right? But thickness of the hydrated mantle is like 30 kilometers in depth. So that volume is enough to storage all seawater into the seawater. And then some calculation were made by Hatakeyama et al. 2017. Their calculation is if hydration of the mantle continuously occurring, so after 600 million years later, all water will be sucked up into the mantle. But we have volcanoes, so like there's so many calculations. But anyway, so this is kind of homeostasis or something like that for the Earth, like to keep water content constant or like losing inside or whatever. But we need to calculate. It's very interesting. But anyway, so this deformation or earthquake or seismicity and then water reaction or penetrating water is very interesting to me. Then, so here, we have earthquakes at the 30 or 40 kilometers in depth. What that means? So usually, the inland earthquake occurs shallower than 20 kilometers. So like, usually earthquake occurs at 10 to 20 kilometers in depth, but here, the enormously low or deep earthquakes, the double. So what we need to think is strength of the plate. This is from the kind of classic, very famous paper from Crust et al. So here, depth as a function of differential stress. At shallower region, so the strength of the plate is constrained by the friction or brittle strength, and which is a function of the pressure, actually. So with increasing depth, rock strength in brittle field or friction field increase like this. But if you go deeper, so temperature will also increase, right? So this means like crystal plastic deformation is enhanced like this if you go deeper. So if you extrapolate the frictional or brittle or seismic strength to this way, and then if you extrapolate flow, like high temperature deformation strength to here, so this line will meet somewhere around here, right? So it's over 1 GPa differential stress. It's too strong to deform the plate. So in the Earth, there must be a mechanism to the plate weaken. Then, so based on this paper, so he connected the frictional and flow line with dashed line because it's very difficult to measure because you need to go high temperature. So you need to go like 400 to 600 degrees C to test how strong at this range. And then you need to measure also very high strength because friction strength getting increase and increase. So that's why he connects this line by dash line. But ideally, we should measure the strength of the plate or strength of the mantle, lithospheric mantle directly at this condition. So that's why, the target of our study is somewhere around here, the mix with frictional and then flow strength. To test this condition, to test the strength of the oceanic plate or around this region, so we newly developed the apparatus actually with Junmuto, who who is in Tohoku University actually. He's not here today, but we built this kind of apparatus. So this is, we call New Griggs rig. So Griggs is an American geologist name, so who built these original versions like 60 years ago actually, but we kind of redesigned, then installed that almost 3 years ago, or more than 3 years ago. So using this apparatus, what we did is simple. We pressurize the rock sample and just press, but at high temperature and high pressure. The sample assembly is something like this. So it's already 16 minutes, so I skip in detail, but the sample is here. So this is green one because we use olivine sample for experiment. We put sample here with oblique surface, and then we push vertically, and then we induce shear deformation like this, originally like this shape, but we apply pressure and temperature to the sample, and then we press like this to induce shear deformation, because most earthquakes is the result of shear fracture, so we apply shear deformation like this. And then we put heater inside of the pressure vessel, and the thermocouple here, and then we apply high pressure. So all these sample assembly are put inside the pressure vessel, which supports high pressure. So we put sample here and apply high pressure, high temperature, and then squeeze. The experimental condition is somewhere around here, 500 and 1000 MPa, so which is roughly the 30 kilometer in depth. And the temperature is 400 degrees C to 1000 degrees C. The strain rate is 10 to minus 5. And then these conditions is kind of scaled to 200 to 600 degrees C in the real strain rate, the nature. To run experiment, we need to prepare these kind of small pieces of the sample. So sample size is 6 millimeter in diameter. So it's kind of small, but to compare the diamond cell, it's large. But anyway, it's small. And then this is typical result. So vertical axis is shear stress, so how much shear applied. And then horizontal axis is shear strain. So this orange line shows the result of olivine at 600 degrees C. And then black line shows a kind of control experiment using quartz at same pressure but slightly higher temperature. So we also measure the kind of ultrasonic radiated by fracturing. We call AE, acoustic emission. We also record it. And then for quartz experiment, so steady state strength is higher than olivine, but there's no AE, so there's no fracture during experiment, just like plastically deformed. Then, but olivine at 600 degrees C and also 800 degrees C as well, we have big sound like even larger actually during experiment. But sample is just 6 millimeter in diameter. But we made large, very loud noise like here. So we expected acoustic emission like this size actually. But actually what we observed is like this, very big sound. And then we also recorded very large stress drop during this big sound. And then another point is we continuously observe these kind of events. They all like these signals, so like continuously like seismic slip happen during deformation. Then, so this is kind of no one observed, not no one, very few experimental results reported in previously. And then why we observed kind of these continuous stick slipping behaviors, we improved the friction or like error or internal friction of the apparatus. So these are typical results of the similar experiment use similar experimental apparatus. So if the typical experiment has huge friction or huge error during experiment, but since we modify the sample assembly, so we almost, I wouldn't say zero, but we reduce very like error or internal friction. That's why we observe very good stick slip behavior. And then we run similar experiment with different temperature and then different pressure actually. And then these are typical results of our experiment. Sample are all Sankaros olivine. And at 400 degrees C, so we have big stick slipping event like this. And even 600 degrees C, which I showed previously, we have stick slip. And even 800 degrees C, we also have stick slip. And at 1000 degrees C, behavior totally changed. And now we have stable sliding like this. And then this is compiled all data. So the bold line is experiment at 1 GPa, that's 1000 MPa, and then CN line shows experiment at 500 MPa. So all experiment shows stick slip behavior. And then if you enlarge this portion, so we observe small stick slip as well. So its stress drop is just 5 MPa. So Griggs apparatus, many people think Griggs apparatus doesn't have such kind of resolution, but we are able to kind of resolve these kind of small stick slip as well. And then this is, now vertical axis is different. So now we calculate a friction coefficient of olivine as a function of shear displacement, how much slip we apply. So rock friction is very simple. Friction coefficient should be 0.6 to 0.85. This is biaxial, but all our results show smaller friction coefficient. So peak friction is roughly 0.5, and the steady, we don't have steady state some data, but the final friction coefficient is 0.2. It's like the friction coefficient of clay minerals, very weak, actually. And then if you take a look at the microstructure recover sample, so we share this direction. We have, of course, since we have big stick slip and acoustic emissions, so we have this kind of fractures. And then if you enlarge these portions, this is a microscope using Thank you very much. Cross-polarized microscope. So here, this is recovered sample, and this is shear zone actually. And then if enlarge a bit more, so grain looks like deformed as well. So we have shear fractures here, but also grains are also slightly deformed. So it's also really mixed brittle deformation and then crystal plastic deformation. And then if you take a look at the shear, inside the shear zone, we have like nanoparticles, many nanoparticles. So like probably during or before stick slip. So the large grain are totally fractured, and then all small grain are formed along the shear zone. And this is a summary of the mechanical data. So horizontal axis is shear stress, and then the vertical axis is shear stress, and the horizontal axis is temperature. So here we have many lines, but this black line shows friction coefficient of 0.6. And then here's friction coefficient of 0.6 at 500 MPa, and here's 1 GPa, sorry. And then here's dislocation glide clip flow here, and then this green line is dislocation climb flow from House and Korsted. And then these two lines are diffusion clip, grain size sensitive clip flow from Yabe et al. So for 1 GPa or 1000 MPa experiment, so peak friction are well explained by the dislocation glide flow while we have stick slip event. And then at 500 MPa, peak strength was well explained by friction, just simple friction, but steady state friction, so we cannot explain anything. And then like, originally I thought this is because of shear heating, but like even the shear heating needed like 400 degrees C if you take a look at the experiment at 400 degrees C. So we cannot still explain, we need to think more. And then if you plot friction coefficient as a function of temperature, yeah, there's similar trend. But anyway, so friction coefficient is very low. At the moment, we cannot explain. And then more circle is like this, so we don't have time. So I skip, but anyway, so if you take a look at the internal friction is also very low. It's like out of the typical friction, rock friction. Then Then if, sorry, it's very busy one, but anyway, so we found very weak friction at the high temperature olivine to compare the low temperature friction, which is friction questions enough, like as low as like clay minerals. So we could explain the outer rise faulting, why it's deep outer rise faulting occurs probably due to low friction of high temperature olivine friction. And then, so, okay, I have only 4 minutes. So actually, now it's real talk of mine. Actually, so now why we developed new Greek apparatus is we want to inject water into the sample directly like this. So this is same sample assembly, but now we are developing powerful pressure system to inject water to the sample, and then we want to shear with wet condition under controlled powerful pressure, and then so initial result is actually good. So during shearing, we are able to make hydrous mineral. Then, but unfortunately, the very funny reaction happen among not only sample and olivine, but also sample and deforming piston and olivine and water. That's why so we made chloride rather than serpentinite. So we need to think good piston or deformation pistons. And then, so this is also preliminary result, but let's take a look at the right figure. So vertical axis is the friction question, and the horizontal axis is the shear displacement. So actually, even if you made serpentine from olivine, friction question doesn't change so much. So this means, so if you make many fault around outer rise region, so strength of plate doesn't change so much. That's why we have many outer rise fault. And then if we have many outer rise fault, so we have many water storage at the subducting mantle. So probably we could lose water or maybe not. So we need to think more about that. So that's it. Thank you very much.